Let's see. So, like one thing you get out of this is something called an energy landscape. And this is where physicists get real non-specific about things. So here I was being real specific. That's the mechanical energy of a mass in a spring, and that's X. Okay? Get ready, because a physicist will go, energy landscape. Done. Right? That's an energy landscape. Physicists won't even put any axes on it. Okay, if you have to have an axis, okay. Well, duh, this is energy. It's an energy landscape. Oh, you have to do a problem? Okay, well, here's some units. There's 0, 1 eV, 2 eV, 3 eV, 4 eV. Okay, fine. Right? And now you probably want an x-axis, don't you? Forget it. We're not giving you an x-axis. We don't put x-axes on things. What are you talking about? So this could be where something is moving in x. This could be the stretch of a bond. We usually call it like a generalized coordinate, and we don't worry about what it is. It's too complicated. We can't get bothered with that. Okay? So here, it was literally the position of the ball. Here, it could be many things. But just to be kind, I will make it the position of an electron. There we go. So now it's something physical. I'm just warning you, you may see, like in a book, you may just see this, or maybe you'll see this. And then you'll wonder what this is. It's usually a stretching bond in a chemical system. Okay? Are this week's lectures on the exam? Yes. So the exam is momentum and energy, but not fluids. So not next week's. Okay, so the things we can learn about this is this ball could be in one of two stable states, right? If you let it roll all day and eventually stop, it's either going to stop here at A or it's going to stop here at B. Right? It's going to be at one or the other. Not moving. And if you were to start getting it moving, it's just like the mass in the spring. When it's trapped in here, just moving with, say, this much energy, it's just bouncing back and forth on whatever this coordinate is. And it's trapped in this well. Just like a ball would be trapped if this were a hill. Right? If the ball is just rolling like this, it has this much energy. Okay? Is it going to get over the hill? No. It's not going to get over the hill. What if I give it this much energy? Is it going to get over the hill? No, it'll never get over, because this is the turning point. It'll only get up to the turning point. La, la, la. What about here? No. How much energy to get over the hill? This much. What if I need a number? It's this much. Right? That difference, about an EV. So if the ball is sitting in a well that's about an EV to this barrier, if you give it more than an EV, then it'll fall down here. Right? So if I say, what's the energy to get from, if you're at the bottom of the well in A, how much energy you need to make it to B? The answer is the height of this. And rather than think about quantum mechanics, you can just think of it as a ball rolling around in a hill. Now, if I give it enough energy to get to B, what's it going to do? Is it just going to sit there? Nope. So there's no friction. It'll say, woo, whoa, all right. And it'll come all the way back down to A, and it'll get back up to here. Right? Now, if it's a real system that's friction and radiating and all kinds of stuff happens, it'll really just eventually make its way back down to B. Right. So one kind of question would be, the energy to get from A to B. That's really it, yeah. Or another question might be, here's a bunch of points. Where do I need to start it over here to make it to there? And the answer would be whichever one is above this barrier. Right? So you could do that whole thing without knowing what this axis is. Because often the questions are just about the energy, or whatever physical thing you're trying to do is just about the energy. Okay? So watch for those.